Hey, Catherine, can you hear me? Hmm, hmm.
I can hear you.
Oh, great. Good. We've got Sally now. Sally, are you great. You're a panelist. Great. So now we're just waiting on Catherine Callis. Catherine, I couldn't hear you, but was that just because you were muted? Catherine Spearin, could you say something? Oh, okay. So we've got both Catherines together. Okay. But Catherine, can you say something? Sally, can you say something?
Hello, hello, hello.
Great. And now just to test, all attendees are currently muted. But Keisuke, I see you are on the line. I'm going to allow you to talk. I just want to make sure you can hear us and that you can see the slides. Keisuke, can you just unmute for a sec? Yeah. And can you say something? Hmm.
Hmm.
Okay, so Keisuke, I've allowed you to talk.
So this is Jarrett. You just unmuted me.
Oh, good.
Can you hear
Okay.
me?
Okay, yeah. Now I guess I'm hearing people and I'm unmuting people randomly. Great. Okay, so this is good. I can hear people in the audience, but if everyone in the audience will now, and can people in the audience, Jarrett, can you just confirm that you see a slide with the Stanford picture on
Yes.
it? Perfect. Okay, good.
And I
Okay.
think we still cannot hear Catherine's burn.
Okay.
And is Catherine Callis going to log on separately or, oh, we lost Catherine altogether. We won't be starting until 12:01 or 12:02. Catherine Callis, I see you raised your hand. Okay, you're now an attendee. I'll promote you. Catherine Callis, can you unmute for a second? Just confirm we can hear you.
Hi, can you hear me?
Yeah, you're good. Okay.
Okay.
Okay. Well, I'm going to suggest it is, how many people do we have on the line? 25. Let's wait one more minute to start.
So Catherine S, can you speak and can we hear you?
Can you hear me now?
Yes,
Yes,
perfect.
great.
Yay.
Okay, great. Okay. All right. So, Catherine, and Sally, when it's your turn to talk, just turn your um, unmute and show us your video. Can you hear me?
Yes.
Okay. So when it's time to talk, just turn your cameras off and unmute, and we'll be good to go. All right. I see that we're up to close to 30 attendees, so I'm going to suggest that we get started. Welcome, everyone. It's great to have you today. My name is Sarah Salter, Managing Director of the Stanford Center for Carbon Storage. And I am joined by Professor Sally Benson, who is the Precourt Family Professor in the Environmental Energy Science and Engineering Department at Stanford University, as well as Catherine Spearin, who is a postdoctoral scholar in the same department, and Catherine Callis, who is a fourth or fifth year PhD student in the department. And the three of them together are going to give you an update on a really interesting project that we are involved in at the Otway Test Center in Australia. And they've got some really interesting results that we think are transferable to many other projects. So without any further ado, I'm going to hand it over to Sally first, who's going to give an overview of the whole project. It's a little bit of its history and what the point of this project is, and also share some results on some pulsed neutron logging work that we have recently completed. She's going to be followed by Catherine Spearin, who's going to talk about some of the core flooding experiments that she's been working on, as well as the impact on heterogeneity. And then finally, Catherine Callis will wrap it up with some results from some really interesting simulation modeling work that she has done. So what I'd like to do for this is have everyone make sure that they are muted. If you have a question, what we'll do is at the end of each speaker, we'll take some quick questions. If you can either raise your hand with that raise hand button that a few people have already used, so we know that it works, or you could put your question in the chat and we'll deal with it that way. So without any further ado, I would like to introduce Professor Sally Benson, and I will stop sharing, and Sally, you can share your screen.
Okie doke. All right. And we will go here. Okay. Continue to share. Okay. All right. Anyway, hi, everybody. You've already heard who I am. Anyway, thanks for joining us for this webinar. We're super excited to be talking about an experiment that we've had the opportunity to participate in over the last couple of years in planning. And then this last year, we were actually able to complete the experiment. So now what we're going to talk about is some very early results from the experiments. Okay, and the name of the experiment is the GeoCquest Field Validation Project. Whoops, here we go. Okay, but before we do that, very important to acknowledge the very, very generous support from BHP, BP, and ExxonMobil, who provided funding for this field scale experiment. And then thanks also to Chevron for funding the Stage 4 infrastructure project. We needed to recomplete a well, and we needed to drill an entirely new well to do the experiment. So thanks to Chevron for that. We'd also like to thank research partner Schlumberger Dole Research Center in the U.S. in the Boston area, who helped a lot with the interpretation of the logs, and also they provided the service for pulse neutron logging, which is really the centerpiece of this experiment. Also, thanks to David Basin and Mitch Allison at the CO2 CRC for their outstanding operational leadership. They've been an incredible partner, and anybody who's interested in doing experiments of this type, the Otway International Test Center has an amazing infrastructure, both in terms of installed equipment as well as very experienced people. So thanks to everybody for making this possible. Okay, so I want to talk first about the motivation for the experiment, what we were hoping to learn, and why we think it's important. And as geoscientists, we all know that geological heterogeneity exists at every scale, from the pore scale to the core scale to the log scale to the outcrop scale, and of course the field scale. And so the questions that were addressed in this work are twofold. First, we wanted to get direct field scale evidence for how multi-scale geological heterogeneity affects plume migration and trapping. And then second, and equally important, we wanted to learn how to develop a practical workflow that could accurately characterize and simulate the influence of this multi-scale heterogeneity on plume migration and trapping. Okay, so just to say a little bit more about the GeoCquest project, this was really the motivation for our interest in doing a field scale experiment from about 2016 to 2024. We worked on a project with Stanford University, Melbourne University, and Cambridge University on a project supported by BHP to really try to, at the small scale, understand the implications of heterogeneity on multiphase flow and trapping. And we began by looking at cores and getting core samples and doing multi-scale flow experiments with visualization using X-ray CT imaging. We then went on and did trapping measurements in a very wide set of rocks that were available, and learned some fundamentally important things about the relationship between heterogeneity and trapping. We then moved on to begin to try to develop the foundation for a workflow for incorporating this kind of heterogeneity into simulation models. Now thinking of the grid cell as the fundamental unit of measurement, and which of course there's going to be lots of heterogeneity, subgrid scale heterogeneity. So we wanted to learn how to incorporate those into those models. The result of that was sort of a generalization in terms of the idea of composite rock types that include both high and low permeability components, which also have different capillary pressure curves. The consequence of this is that the relative permeability curves are now going to be directional, meaning whether they're aligned perpendicular or parallel to the direction of the laminations, the relative permeability would be different. And also we learned that the relative permeability curves would be flow rate dependent, though that's not the primary focus of the work today. We then developed a methodology to incorporate this information into highly resolved models, and then went on to do full physics simulation, including multiphase flow and geochemistry, and then also did some work on reduced physics models. So all of this workflow was developed as a result of this collaboration, and we thought we were ready to test some of our ideas at a field scale. But before we jump into that, I just want to say a little bit more about this idea of these directional relative permeability curves that are characteristic of composite rocks. Up here you can see a layered system with high permeability and low permeability units. And for the case where we have flow of CO2 and brine perpendicular or parallel to this, we will get one particular type of relative permeability curves. So in the case where we're at the viscous limit, meaning at a high flow rate, the layers aren't terribly important. And as a matter of fact, if you go to high enough flow rates, the saturation will be the same everywhere, and you'd get relative permeability curves like these red ones, much like you would expect for a homogeneous rock. However, if you conduct the experiments or the flows are at much lower rates, where now capillary forces are going to dominate the saturation distributions, what we'll find is that our relative permeability curves, as shown by these blue dashed lines, they've shifted to the right from the red curves. The consequence being that we suppress the mobility of water and we enhance the mobility of the CO2. So parallel to the direction of the laminations, we expect CO2 to move faster and water to be less mobile. Now, if we take that same composite rock, and now we consider that we're flowing perpendicular to those layers, that again, if we went to the viscous limit, we would have the red curves, but in the capillary limit, again, where the saturation is determined by the capillary pressure curve, what we see is that the mobility of water is higher than it would be in a homogeneous in the viscous limit, and also that the mobility of CO2 is very suppressed. So what it means is that these composite rocks are likely to retain CO2 much deeper in the formation because of the low relative permeability curves perpendicular to the direction of the laminations. So as we go on, this will be a key feature. Okay, so you might be saying, okay, well, that's interesting. You know, academics who like to do interesting things, that's true. But it actually turns out to be very important for field scale uh, plume migration and trapping. And I'm just going to give you a really quick example. This is some work done by Richard Larson, a PhD here at Stanford, who's just beginning his studies. And I'm going to go through a sequence of simulations. I'll show them to you. The first one we'll have as a base case, very traditional simulation. Actually, we are not even considering relative permeability hysteresis here. The second case will add in relative permeability hysteresis. The third case will, in addition, include capillary heterogeneity, that all the rocks have different capillary pressure curves. We'll then go on to look at anisotropy associated with the composite rocks, and then finally, directional relative permeability, and then a case where with even a little more detail than that. Okay, so we're going from sort of how we might have done the simulations quite a while ago to sort of really state of the art that incorporates all these features. And again, really, I think makes the point why this kind of work is important. So what we see here is the CO2 migration 30 years post-injection for a field scale project, injecting 1 million tons a year, sort of typical CO2 storage simulation. And what you see is in the case where we have no hysteresis, just single valued relative permeability curves as a function of saturation. We're injecting deep in the system, but the CO2 plume rises to the surface and spreads out under a very slightly dipping seal. So you end up with a very large plume that's in direct contact with the base of the seal. So now if we add hysteresis, so in essence, we add residual gas trapping, you can see that, indeed we retain quite a bit of the CO2 deep in the system, but nevertheless still develop a gravity tongue, which is going to move up gradient. If we now add capillary heterogeneity, we see an even larger fraction is retained deeper in the reservoir. If we then add anisotropy, we see that again, CO2 is retained deeper in the storage reservoir, or limiting vertical migration. And then when we go to the case where we include directional relative permeability, you see that, in fact, the plume actually never even makes its way to the base of the seal and spreads out deep in the storage formation. And we get similar results for the rock types. So basically, the point is, if it turns out that the directional relative permeability manifests itself at the field scale, this could be very important for storage security, plume immobilization, and risk reduction. So that's why we're doing this experiment. So now let's just jump right into the experiment. So what we did is we went to the Otway International Test Center, a little schematic of that on the right-hand side here. We injected 10,000 tons of a mixture of CO2 and methane into the well CRC3. We did this over a 72-day period at 143 tons per day. And what we wanted to observe in particular is what was the saturation distribution at this well CO2 CRC8. Okay, so in addition to measuring the saturation continuously at CRC8, there was also VSP and passive seismic monitoring done by the team at Curtin. We won't be talking about that work. And Wright from Japan also made some strain and temperature measurements with behind the casing fiber. So this is really a very rich data set, but again, we're going to focus on the saturation monitoring. And then after the injection stopped, we basically continued these measurements and then began to add geochemical sampling at CRC3 so we could also look at solubility trapping. So that is the experiment, and sort of simply put, our hypothesis is that if the multiscale heterogeneity processes had the effect we would expect, is we would expect that the CO2 plume migration is faster between CRC3 and CRC8, that on average we would have lower saturations than we would expect for a homogeneous reservoir, that we would see much more of the CO2 retained deeper in the reservoir. And then with regard to the imbibition phase, we expected faster plume immobilization and that a higher fraction of the CO2 would remain trapped. So that's what we were expecting. And it's a little schematic. What we would expect to see if all of these things were true is that we would have very rapid breakthrough at CRC8, and the saturation distributions would be highly variable with high saturations in the most permeable units and low or no saturations in the intervening units. So our experiment was really designed to get a world-class data set that would show us whether or not this kind of phenomena was happening. So for those of you who are not familiar, here's a schematic of the Otway International Test Center. 8 wells instrumented with pressure sensors, fiber behind casing, orbital vibrators, just an incredible sort of basic toolkit, along with a source of a gas mixture of CO2 and methane, as I described before. The system, the unit that we studied was the Parate Formation. I'll say a little bit more about that in a minute. And here's just a little map view of the site. So here's CRC3, and about 115 meters away, we have CRC8. And then here are some other wells, again, where pressure was monitored and that were also used as part of a seismic monitoring program. Yeah, so we're injecting in CRC3 and looking at saturations in CRC8. So in terms of the formation, we had very extensive characterization. It's basically delta front depositional environment with distributary channels, mouth bars, and carbonates. And these are carbonate cements. They're not like reef-like structures. We had open hole logs from CRC3 and 8, and also access to all the other data. We had continuous core in the injection unit that we were interested in. We had mini permeameter measurements along the length of these cores. Also routine core analysis for permeability. As you'll hear about from Catherine Spirin, we did special core analysis and also chemiscans on those cores. So here's pictures you can see. Here's the CT scan of the core. Here's actually a photograph of the core. And just to give you a perspective on the scale of the heterogeneity, this is just a little 1 meter unit within our 10-meter thick injection interval. You can see a tremendous amount of heterogeneity of a number of varieties. We've got laminations, heteroliths, and so forth. And just to sort of put a fine point on how heterogeneous this is, even if we built a simulation model with 1 meter grid resolution, which many would judge to be a highly resolved model, tremendous amount of subgrid scale heterogeneity. So in other words, we got what we want when we were able to access this interval. Okay, so moving along a little bit more about the injection. So here's CRC3 schematic. This well had been used for a prior injection in the unit PS1 that was packed off and isolated from this PS2 zone, Parati 2 zone. It's here where we did injection. And then in this upper zone, we also had pressure sensors and the capability for fluid sampling there as well. So this is a picture of the bottom hole pressure buildup in this zone here. As you can see, there was a rapid pressure buildup, but then stabilization and a gradual decrease. These fluctuations here are associated with some challenges on the compressor, but overall we had a very excellent clean injection of average of 143 tons per day. So that was the experiment. As I said, this is a work in progress. We've been working on simulation and history matching. The primary simulator that we're using is something called GEOS, which is a collaboration between Total Energies, Lawrence Livermore, Chevron, and Stanford. It's very fast, multi-physics, open source, and yeah. And we've built highly resolved models, as you'll hear from Catherine Callis. And thus far, we've primarily focused on a two-component, two-phase simulation that's similar to the Eclipse 300 equation of state. And in addition to doing this, we want to do history matching. And so we decided to build a machine learning model for both pre-injection planning as well as for post-injection history matching and so forth. And Catherine Callis will talk to you more about that today. And on the right-hand side, this is just an overview of the system. And again, we modeled this very small region with 4.5 million active cells of 3 meters by 3 meters by 0.3 meters thick. So a very, very highly resolved grid. And yeah, so in terms of the rest of the time today, I'll show you the pulse neutron log saturation data and talk about our analysis. Catherine Spurn will then talk about some of the core flooding work, and Catherine Callis will talk about simulation. So I guess I will stop here for a minute and ask if there are any questions. And
Yeah, if
while
there are any
I get up.
questions, use the raise hand button at the bottom of the screen and then I can unmute you. My understanding from Catherine is that the chat function might not be working. So if anyone has a question, just use that button that's the raise hand, looks like a hand. Not seeing anything, Sally, so I think you can go on.
I can just go on. Okay, good. Yes, all right. So let's talk about the pulse neutron logs. This work has been led by Aman Raizada, again, a PhD student at Stanford University. Well, here we go. Okay, so this is just looking at a cross section between the injection well CRC3 and CRC8. Again, 115 meters apart. And as you heard, we wanted to get a very highly heterogeneous injection zone. So we weren't looking for the nice permeable clean sands. We were looking for a zone like this, and in fact, we got a zone like this. So here's again the injection well. You can see a number of high permeable intervals, 3 to 4 in the injection well. And similarly, if we look up dip, there's an offset of about 11 meters. You can again see, a number of high permeability zones that are intersected by this monitoring well. You can also see the presence of some carbonate cements, which locally appear to act as good seals. Okay, so just to say a little bit about the pulse neutron program, again, we were really relying this on our major way of understanding the effect of heterogeneity and helping to do history matching and validation of the workflow. Uh, there was a competitive process by CO2 CRC. In the end, they chose the Schlumberger pulsar tool for the time-lapse measurements. Again, what was really unique is that the rig was on site for the entire time, and the contract was for daily logging services. So we were able to do logging for every day that the rig was operational, which was the majority of them, 131 out of 151 rig days, we were able to get the pulse neutron logging data. And in terms of the sort of attributes of the program, we decided that we were going to run the log very, very slowly, which would give us, good counting statistics on the nuclear measurements themselves. Also, it would help us with really excellent depth matching, which turns out to be absolutely key to getting high quality time-lapse data. And yeah, and again, given that we wanted to see these very thin layers, this was very important. We used standard and developed some new methods for doing this alignment between multiple passes. And so every day we were able to get 3 passes, and then for the baseline we had 4. So in total, we had over 400 PNL logs to develop this benchmark saturation data set. We measured the full suite of measurements, including sigma, T-Phi, FNXS, and full spectroscopy. We have thoroughly processed the sigma and T-Phi and are beginning to explore some of the other passes. Okay, so what we really wanted to know, a key part of the hypothesis is that the CO2 would quickly migrate from the 115-meter difference between the 2 wells. And so we really wanted to make sure we could detect a first arrival. These have never been seen because typically, you maybe come out every 6 months, maybe if you're lucky, every month to look for saturations. And so you don't necessarily see the plume come through. Since we were there every day, measuring 3 logs a day, we had a high degree of confidence we could see this. So we wanted to develop a robust statistical test of the first arrival. So that's what this slide shows. We don't need to go into any detail, but the key thing is that we were able to show that with a 95% confidence interval, if this T statistics basically exceeded a value of 2.57. So everything within this band, okay, so here's depth and here's this T statistics, everything within this band is statistically identical in essence. But once it crosses this threshold here, we have 95% confidence that the arrival has been measured, and we think that our sort of detection threshold was about 5% on average. So what we saw is that as early as November 14th, we began to see the first indications that CO2 had arrived at the monitoring well, and by 5 days, it had arrived in multiple layers. So yeah, so very, very fast. That traveled in that 115 meters in just a couple of days. So this is just a little bit more looking at, this is the first breakthrough that we saw. So this was on November 14th. And basically the way to read these curves is that when there's a separation between the baseline and the subsequent time-lapse data, that's an indication that there's CO2 there. The one on the bottom is statistically significant. The next day, again, you can see that over this nearly 2 meter interval, we're starting to see CO2. And we think this heterolithic unit here is where this was traveling in. And from the geologist's log, this makes sense because it was actually a gravelly zone there. Okay, so that was just the first arrival. Now this is a representation of the entire data set plotted every couple of days. So now this is depth on the y-axis, and on the z-axis, this is time. And again, here you see on November 14th, beginning to see these first arrivals. Then it starts showing up in multiple intervals. Over time, it grows. You can see interesting features like this little blue band here. This is a place with low permeability, potentially carbonated cement, and so forth. So the first period here, this is the injection. After about a month or so, we saw the saturation stabilize, which is actually what we would expect. We then turned off the injection, and to the right is the recovery, and we were only able to monitor for about a little over 2 months, and we saw some signs of imbibition, but actually not much. So we can get back to that later. Okay, so this is just another way of presenting this same data as a heat map. So this is, again, depth here. The colors correspond to the saturation that was measured at those varying depths and how that changed over time. Again, you can see the first arrivals here very early, just 4 to 5 days after the injection began. You see gradual buildup, and again, we see a number of layers. So here we have layer 1, 2, 3, 4, and 5, and I'll show you those in a minute. Okay, so this is the same information. So now this represents the average saturation in the interval. And as I said, that after about a month or so, the saturations stabilized and remained pretty stable for the first 2 months after injection stopped. And then we can look in the bottom here at some of the individual layers. So this would be layer 1. We have layer 2, and so forth. So we can see that the saturation, or the average saturation in each of these layers was also very different, indicating the importance of capillary control on saturations. Okay. So yeah, just a little bit more making this point. So if this were a gravity-dominated system or a buoyancy-dominated system, we would expect to see high saturations of CO2 at the top of this layer and low CO2 saturations at the bottom. Instead, we see just the opposite, and we interpret this to be the consequence of a fining up sequence with very high permeability, low capillary pressure at the bottom, and finer sediments at the surface. Okay, yeah, we're going to skip this one. So just one more piece of data that I like to show. So this is the saturation at the injection well. We could not do this during the injection itself due to the complexity of the completion that allowed us to have individual zones isolated. So this was done immediately after injection stopped, a day later, and then a week later, and then about a month later. So here you can see this is the where it shows red. This is where CO2 is present. So you can see the injection sorted itself into 4 primary injection zones. And interestingly, if we look sort of near the end of this, like a month after injection stopped, we do start seeing an indication of some imbibition occurring at the injection well. So that's that. And yeah, so just briefly, what have we learned from the data? That the CO2 migration is faster. Check. Yeah. Average saturations of CO2 lower. Yes. Lots of CO2 retained deep in the reservoir. Yes. And we, haven't yet observed clear indication of imbibition and subsequent residual gas trapping. We think that will take longer. And similarly, we can't make any direct conclusions about trapping efficiency. And there's really so much to learn because such a rich data set and particularly on workflows to characterize and model these highly heterogeneous formations and how do you parameterize them to put those in models. But we'll be hearing more about that. And I'm going to wrap this up and we can answer any questions and then also turn this over to Catherine Spurn.
All right, before we turn it over to Catherine Spurn, I'd like to see if there are any questions. There's a little raise hand emoji down at the bottom of your screen. Just click on that if you have a question. Maybe if one person would, okay, great. We've got a question from Wayne Rowe. So Wayne, I will unmute you. I will allow you to talk. Can you unmute, Wayne? And then you can ask your question. Perfect.
This is outstanding work, Sally. Very important too, some of the results that you're showing there. I do have one question though, where the work that you did on the time-lapse pulse neutron logging, you were able to use the same advanced, the latest generation of pulse neutron in the experiment. In reality, there's going to be, especially as time goes on, there's going to be older technology where the baseline was acquired and using newer technology as the years go on. Is that something that you had considered and talked about in your experiment on how you would handle that?
Mm-hmm. We haven't yet. So, but just a little bit more on the older and newer technology. What we found most useful here was the Sigma log, which we didn't expect because it's pretty fresh water. However, when you go really slowly and you have these great statistics with the time-lapse data, um, it's it's very high quality data. So if you look at the older technology, it's basically that's what a lot of people were measuring. So if you have confidence in those measurements, yeah. But the general issue of, changing tools and really old data is, it would make it problematical to do this kind of detailed analysis. And honestly, I'm not sure, anybody from a very, I don't think that for an industrial project, you want to go out and measure saturations all the time. It's, costly. But I do think that early on in the projects, looking at seeing in detail how the CO2 is moving could be really beneficial for helping develop a much clearer understanding of the rock properties and how they're interacting with the injected fluids.
Well, that's a great point, and I'll make note of that. Thank you.
Great.
Thanks.
Okay, I see we have one more question from Lynn Orr. So Lynn, I'm going to allow you to talk. If you could unmute.
Yeah. So Sally, this is, of course, I'm hugely interested in this, and I wonder, a question that's been in our minds for, well, like decades now, is how much crossflow takes place. And this is hard to observe, and I'm not sure whether any evidence, yay or nay, can be seen from the data that you have. But maybe the combination of flow simulations that use all your detailed characterization, and then and that do a reasonable job of matching the observed performance of the pilot could then be used to ask the question: Do you see any sort of transverse migration from the zones that are conducting the flow? I mean, it seems to me that the message over and over again here is that heterogeneity is our friend, For those of us who are reservoir engineers, all the things that caused us headaches and heartaches are now working in favor of getting the CO2 widely distributed where it could be dissolved in all the water that's all around it. And so anything you could do that would take a look at that transverse flow question, I think would be very interesting.
Hmm. Well, good. Yeah, I completely agree. I mean, we have a little bit of information on that in that, remember there were two zones that were packed off and there was a shallower zone above the injection zone. We have the pressure measurement in that, and that went up about 10 psi.
Well,
And
okay. So there is some evidence of certainly with
there is,
communication, but pressure is different from a lot of flow, although I guess it's
right.
connected because of through the
So,
pressure
so
gradient.
Yeah, so one would need to, try to see how much information there is in that pressure transient that could distinguish, is this brine flow? Is it CO2 flow? Is it flow through sort of a uniformly low permeability layer? Or was there a little break in the layer that allowed CO2 to go up? There's so many questions, but we have high hopes from the team at Curtin that they will be able to figure out, some of those questions that we could not observe just based on the data that we had. But yeah, no, I think you're absolutely right. And, we hope to do that. And, if we were able to do an experiment again of this sort, it would be great to add some more pressure monitoring that could specifically try to get a handle on some of those things like crossflow.
Cool.
Yeah.
Great. Okay. Well, thank you so much, Sally. I think we'll move over now and hear from Catherine Spurin, who will talk about some of the core flood experiments. Great.
Great. Can you hear me?
Yes, we can hear you.
Okay, great. Let me just share my presentation. Can you see the presentation in the right mode?
Yes, it looks great.
Okay, great. Okay, thank you. So basically today I'm going to be discussing the core flooding experiments and looking at the influence of small-scale heterogeneities on these experiments. So I'll just get started. Here we go. So we were sampling a really wide range of heterogeneity at the Otway site. And so this image on the left is something that Sally has already shown, but it's basically all the logs from our monitoring well, CRC8. And you can see on the right-hand side is the core that was extracted from this well. And here the green and the white dots are the places where our cores that I'll be discussing in these experiments today were taken. And so we took a total of 10 samples over a range of about 15 meters. Some samples were drilled horizontally, so like in the direction of flow, and some samples were drilled vertically, so perpendicular to the movement of the CO2, and that's just denoted by these little V's. And these vertical samples were drilled in locations near a horizontal sample so that we could have pairing both horizontal and vertical. All samples were 5 centimeter in diameter and between 5 and 10 centimeters in length. And we performed a series of experiments at high pressure and high temperature to mimic reservoir conditions. And so just as a note, our highest resolution reservoir model that Catherine Callis will be discussing in a bit is 0.3 meters or 30 centimeters. And so you can see that these samples and everything that I'm going to show you in this presentation is below even our highest resolution reservoir model. We saw large variations in permeability, which really highlight the heterogeneity of the site, and that is shown in this figure here. So on the y-axis, I have the depth in meters, and on the x-axis, I have the permeability in millidarcies. And so you can see the permeability with depth on this figure, and I have it for 3 different measurements. The mini permeameter, which was done on the core extracted, and then the SUN, that was this routine core analysis in green, and then the scale, which are our experiments shown in orange. And then you can kind of see that we have some with really high permeability and some with very low permeability in this work. So just a brief overview of these multi-phase flow experiments and how they were conducted. Basically, our sample sits in the core holder here, and our sample was initially saturated with carbonated water. We did this because for these experiments, we're not interested in any dissolution dynamics. We're just interested in like the physics of the flow. Then we injected the CO2 saturated water and CO2 from these pumps here at a range of fractional flows. And then we measured the pressure drop across the core. And so we were doing all this imaging at steady state and getting steady state relative permeability values. And we got the saturation by using a medical CT scanner, so imaging the CO2 across the core. And for this, we had a resolution of about 0.5 millimeter. So one of the first things that we observed in this data was very large variations in permeability, even for a very narrow range of porosity. And so what I'm showing on this figure on the left-hand side is the porosity on the y-axis and the permeability on a log scale on the x-axis. And so what you can see is we have a very narrow range of porosity going from about 19% to 35%, but our permeability is going from less than a millidarcy at about 0.2 all the way to over 1,000. And we saw some cases where basically the porosity and the permeability weren't very well correlated. And one of these examples is shown on the right-hand side. So here I'm showing the porosity map for one of these cores. And you can see that we go from a porosity of 0 to 40% on the color bar. And basically there seems to be good porosity, about 20%, and no obvious barriers for flow. But actually the permeability for this was 0.2 millidarcies, and we were unable to do a flow experiment for this core specifically. And we think the reason why we don't have a great correlation between permeability and porosity for some of these samples are that there are some features below the image resolution of our clinical CT scanner. And so what I'm showing on the right-hand side now is a micro CT image of one of our cores with a resolution of about 10 microns. And you can see these really bright white fine layers, which are actually barriers to flow, which we weren't able to image with the medical CT scanner. We saw extreme heterogeneity. So for this slide here, I'm showing one of the vertically drilled cores on the left-hand side, and its horizontal pair that was drilled about 20 centimeters away on the right-hand side. And so you can see that these two rocks look very different. We have different spacing in the layers, we have different porosities, and we have very different permeabilities. And this was the case for all our horizontal vertical pairs. So this is another example of a vertically drilled core on the left-hand side, and then a horizontally drilled core taken just 20 centimeters away on the right-hand side. And so we weren't really able to have these vertical horizontal pairs just because there was so much heterogeneity, and even taking a core that was 20 centimeters away led to a very different distribution in these like layers and in the flow of the fluids. And so this slide is basically showing the CO2 saturation at the end of drainage for all our horizontally drilled samples. And the first thing that you can notice is that no two samples look the same. And so we have some cases where the CO2 is traveling in these thin layers. For example, this one, GFV 14, or this one here, GFV 15. We have some cases where it's the extreme channeling of CO2, for example, GFV 8. And in some cases, we had more tortuous pathways, like this one on the top right-hand side, GFV 12. And actually, the CO2 was able to go across the whole core. It's just quite hard to show with a single slice what that looks like because the pathways are so heterogeneous. On this slide, I'm now showing all the vertically drilled samples, and you can see again that no two sample really looks the same. We have some cases of these very fine layers, for example, GFV1 or GFV7, and we have some more complex patterns of heterogeneity, for example, GFV9 on the bottom right. So for the interest of time, I'm going to do a deep dive just on two cores, and I've chosen GFV5 and GFV15 for this. The reason that I chose specifically these two cores were that they're from the same facies and they were taken 3 meters apart. So in the reservoir model, these cores would be modeled with the same parameter. And so now I'm showing the different fractional flow steps where I'm increasing the flow rate of the CO2. And you can see at the end of the drainage here, the difference between GFV 15 and GFV 5 on the right-hand side is quite different. And then at the end of these experiments, we did a water flooding to get the trapping. And you can see again that these cores look very different and the trapping efficiency is very different. So if I just scroll between the end of drainage and the end of water flooding, you can see that the two cores behave very differently. And we can see how that is manifested in the relative permeability. And so for these plots here, I'm showing the relative permeability for the two cores. And you can see that the shape of the curves that go through the points are quite different. For all these experiments, we saw very steep water relative permeability curves. So even at very high water saturations, the relative permeability of the water was low. And something that we saw for all our experiments was very low CO2 saturations. And this is because of channeling of the CO2. So while the CO2 saturation is high in the channels that it's flowing in at about 50 to 60%, when you average across the whole core, you're not seeing saturations greater than 10 or 15%. We can also see the impact of heterogeneity on the trapping efficiency. And so what I'm showing here on the x-axis is the initial saturation. So this is the CO2 saturation at the end of drainage. And on the y-axis, I'm showing the residual saturation, which is the saturation at the end of the water flooding. And I'm showing this on the left-hand side for GFV 15, which is a horizontal core, and on the right-hand side for 9V, so a vertical core. And you can see that the trapping efficiency is very different for these two samples. On the left-hand side, we have great trapping, where all our data points are close to the one-to-one line, which means 100% trapping. And then for the vertically drilled core, we actually had much worse trapping. And you can see that those points now fall below that one-to-one line. And so this is the trapping efficiency plots for some other cores, just to kind of show you that variation that we saw. And I can take the trapping efficiency and plot it against permeability, which I have done on the right-hand side. And you can see that the trapping efficiency is highly correlated to the permeability of the sample. So more permeable samples have a lower trapping efficiency. And so what this means is that the locations where the CO2 would prefer to go, so the more permeable parts of the pore space, actually lead to a lower trapping efficiency than some of the tighter samples. We also did some capillary pressure measurements, so extra characterization of the rock cores using MICP, so mercury intrusion capillary pressure measurements. And again, you see that the heterogeneity is evident. So for these plots, you can see that the entry pressure, depending on the sample, varies from about 10 psi to over 100. And we can see some really huge differences. And I just wanted to highlight one today, which is GFV 12, which is the orange line, and GFV 13, which is the brown line. And you can see that these two samples, which are actually both located next to each other and are both regions where the CO2 was observed in the pulse neutron logs, they have wildly different capillary entry pressures. And so you can see basically how heterogeneous this site is and how much variation we're getting. So with that, I'd like to wrap up. And so our main conclusions are we saw extreme heterogeneity in all the samples with large variations in permeability and trapping efficiency, even for samples from similar depths or the same rock type. We saw that the vertically drilled samples had very distinct properties. And in all our experiments, we did see very low CO2 saturations and very steep water relative permeability. The gas saturation was high in localized areas due to channeling, but this made it difficult to upscale some of our relative permeability values. We see that when we incorporate these relative permeability curves into the reservoir models, it has a large impact on plume arrival, which Catherine Callis will discuss. And we also saw a wide range of trapping efficiencies, with the trapping efficiency decreasing as permeability increased. And so, yeah, we want to thank you, everyone who is involved in this work, particularly CO2CRC. Yeah, and with that, I can stop sharing. And if people have any questions, I'm happy to answer them.
Okay, I see that we have a question from Mike Bennett. Matt Bennett. So Matt, I have yeah, if you could speak. So, Matt, you appear to be unmuted, but we can't hear you. Does anyone else have a question? If so, please raise your hand while Matt. So, Matt, I've given you the permission, and as well, you appear to be unmuted, but we definitely cannot hear you. Maybe what we will do, Matt, if you could hold on to your question, perhaps you could figure out what's going on with your microphone, and instead we will move on to Catherine Callis to speak about the simulation work. All right, Catherine, over to you.
Okay, great. Thanks, Sarah. Okay, great. So today I'll be talking about the simulation work we did before injection began and the machine learning model that was built. So as Sally and Catherine have discussed in length, the GFV project, one of the main focuses was trying to understand the impact of small-scale heterogeneity. And specifically, this work will try to tackle the question of can a practical workflow be developed to accurately characterize and simulate the influence of multi-scale heterogeneity on plume migration and trapping. We have extensive data from the site, from the different wells, we have seismic, but despite that, we still have geological uncertainty, which can lead to significant variations in our numerical modeling results. And so one way to try to combat this is by running hundreds of different simulations in order to try to capture that uncertainty. However, this can be a very expensive and time-intensive process. Here is an example of one of the geo models. So this is again 3 meters by 3 meters by 0.3 meters. We have our facies model, porosity model, and permeability. And the area that we're focused on is this region between the two wells, CRC3 and CRC8. And we're looking at the bottom half of these images here into that reservoir that we're specifically interested in. And we can see that there is quite a bit of heterogeneity just from these cross sections. So in order to address this question and try to capture this uncertainty, we wanted to develop a tool that could be used for pre-experiment planning, history matching to the P&L data, as well as uncertainty quantification. So this led us to creating a machine learning model for our site in order to address these three needs. And the work today will just be focused on the pre-experiment planning. So previous work has shown that machine learning models can provide a faster alternative for solving multi-phase flow problems. So that in 2021, Dr. Gogo Wen, who is a former member of the Benson Lab, showed that a convolutional neural network would provide fast and accurate results for multi-phase flow problems. Since then, there's been a variety of different models that have been proposed as alternatives for traditional numerical simulators. And one of these is a UFNO model, which is a U-Net Fourier neural operator model, which is shown in this work, also by Dr. Gogo Wen in 2022, showcased that it could have superior speed, accuracy, as well as data efficiency, and excellent performance in CO2 and water multi-phase flow problems. However, we couldn't directly use this data set that had been developed in this work because of three main reasons. So we have the super fine grid resolution that's been mentioned, which is much finer than any of the grids that were used in these data sets. We also wanted to incorporate the impact of directional relative permeability curves in order to reflect the highly heterogeneous rocks that we see at our site. And we wanted to include the composite rocks, which Sally had mentioned that from the previous work from GeoCquest in this training data set. So therefore, that led us to developing our own new data set specific for the site. So in order to generate this training data set, we ran over 500 cases using Eclipse E300 CO2 store. We injected 10,000 tons over 67 days and monitored for 60 days post-injection. We have the superfine grid resolution, which results in about 4.5 million active grid cells. And we've included these different rock types that we're sampling the parameters of in order to generate additional realizations. So these distinguishing features we're hoping will allow us to capture the impact of these small-scale heterogeneities in this machine learning model. And in total, to generate the training data set, it took about 1,500 days of runtime and about 15,000 CPUs, which is a pretty intensive process. So the procedure is we have our 4 different inputs. On the left-hand side, we have our horizontal permeability, vertical permeability, porosity, and composite rock type identifier. We use these inputs and train and eclipse, and we generate our saturation over time outputs. And then we use these input-output pairs to train and serve a machine learning model. As I mentioned, we decided to use a UF&O model here, and we can see the results on the left-hand side for 3 different realizations. So we have our horizontal permeability input on the top row, our ground truth saturation at a time step of 25 days, and then our prediction on the bottom. This model was able to achieve 6% test relative error and a 3% training relative error using an L2 loss metric. And we were able to achieve an R-squared greater than 97%. So here we have 2 realizations, and then on the left-hand side, we can see again our ground truth on the top row, our prediction in the middle, and then the difference between the 2 in the bottom figure. And we can see that the prediction is doing a good job of capturing the saturation and plume migration from our ground truth. We're not seeing new grid cells invaded that we don't see in our ground truth, and we're not missing any grid cells. So the only difference here is the actual saturation value. So one of the key reasons that we wanted to use a machine learning model is because of the run speed up time. So this model was able to achieve an 80,000 times average speed up in runtime. Our Eclipse runs were parallelized on 30 CPUs on one machine and took anywhere from 2.5 to 5 days to run for each simulation. In comparison, our UF&O model is able to achieve the same time steps in about 2.6 seconds. So it can be a really powerful and helpful tool in the pre-injection planning when we want to see the impact of different configurations of reservoir properties and understand the impact they have on the output saturation. So one thing in the pre-injection period we were very concerned about was seeing CO2 at our monitoring well during our experimental time frame. And so in order to try to address this, we created a figure here, which is the probability of CO2 present. So the dark red indicates that you have high confidence, greater than 95% chance that you'll see CO2 in those grid cells at this time step. The dark blue is a less than 5% chance that you will see CO2 in that grid cell. And so if we look at the plume, we can see that there's 3 main layers that the plume is migrating towards the monitoring well in. We have a top layer, a middle layer, which is the fastest, and then a bottom layer. So at this particular time step of day 23, we were able to have 80% confidence we would see CO2 at CRC8 in this time frame. So we can also look at how this evolves over time. We can see that that middle layer is moving the fastest, followed by the bottom. And then we actually see in a few small cases that top layer begins to break through a discontinuous carbonate cement layer and start migrating upward. Another thing we wanted to understand was what would the saturations be at our monitoring well in order to make sure our P&L data would be able to capture that. So on the left-hand side, we have the probabilistic gas saturation, so the same graph we were just looking at, just specifically at CRC8. The right-hand side is the average predicted gas saturation. So here we can see at a depth of 1440 meters, we have 80% probability we will see CO2, and that CO2 will have a saturation greater than 20%. And so this is good for us to understand because the P&L required a minimum saturation anywhere from 2 to 5% in order to be confident that we actually have CO2 that's being detected. And so this is well above that threshold, so we have confidence that our monitoring program would be able to identify the CO2 at CRC8. So in conclusion, a machine learning model was used for the pre-injection planning period. It had superfine grid resolution, composite rock types, and directional relative permeability curves. Our model was able to achieve an 80,000 times speed up with about 6% test relative error. And we were able to have high confidence that we would see CO2 at our monitoring well with adequate saturation during our experimental time frame. So future work, we're working on the model still, and we are developing a post-injection model that will be able to be used for history matching to our P&L results. So thank you for listening, and thank you to our funders. Happy to take any questions.
Great. Okay, I see we've got our first question, which is from Yifu Han. If you could just unmute, Yifu.
Can you hear me?
Yes.
Okay, thank you. Nice work. So I'm curious for your machine learning model, it looks like it's a 2D, right? Because based on the results, so you are predicting the 2D saturation plumes. So
It's a 3D model. I just
Mm.
took the cross section for ease of our viewing, but it is 3D. It's predicting the entire grid.
okay, I see. And how you compute the relative error?
So I used an L2 loss, which Dr. Gogo Win in her paper had found it had a better predicting capability than just MSE, but it's just a relative error still.
I see. Thank you.
Catherine, is it the plume error? I think it's the plume error.
Mhm.
So it's sort of a more rigorous test because there's so many parts that are zero, right? And you don't want to sort
Yeah,
of take credit for predicting. So it's just the plume error. Yeah.
I see. Yeah, got it. Thank you.
Ishtar, could you please unmute and ask your question?
Can you hear me?
Yes.
Yes.
Okay, so I'm asking Matt Bennett questions, not mine. So this is for Catherine Spurring. So he was asking on slide 14 from Catherine if the permeability entry pressure results that you mentioned, if you've seen a correlation between the capillary entry pressure and the sample permeability.
Catherine, we can't hear you.
Maybe I'll answer it if you don't, and if I get it wrong, Catherine, put some nasty thing in the chat. Yeah. So when we compare the capillary pressure curves to the core sample, the big core sample, the permeability of that, we don't really see any correlations. But we understand that we can actually use the capillary pressure data itself to estimate permeability based on like the pore throat, pore size distribution. And we just haven't done that yet, but that's a work in progress.
Any other
I may
questions
just follow
for?
up.
Yeah,
Just I
Ishtar.
follow up on that, Catherine. So when you say on the big core is the RCA, the big one that you were doing the skull, but those mismatch was particularly seen in the samples where you see a lot of heterogeneity in the CT scan. Is that the case?
Right. Yeah, absolutely. Yeah. And it's so hard to actually get the little, so we're measuring permeability on something that's what, 2 inches by 4 inches. The MICP curve is on a teeny little piece of the rock that's from the end slice. And is not representative of the whole rock in any measure. Yeah.
Great. Okay, I see we have a question from Vladimir Kazai. Vladimir, could you please unmute and ask your question?
Yeah, hi, very nice talk. I had a question to follow up about the phenol generalization ability, and the question relative to that, also the uncertainty quantification question. Like, you simulated 500 scenarios. Would the uncertainty maps would they be very different if we just use like naive frequentist approach, like we calculated in how many cases the CO2 propagated that far, and then calculate the fractions and build the maps that way without any FNO training?
I think I understood your question, but let me know if I don't answer it. Yeah, I mean, having the 500 training data set is a very, also rich resource. You don't need to train a model. However, you're still, I guess, pinned into those particular discrete properties that you chose. So I think you can gain a lot of information just from the training data set. I think the benefit of having the model is then if you want to start changing things. So this is something we're focused on in the post-injection period, but changing the conditioning at the wells, or changing our relative permeability curves. If we've sampled that space, then we don't have to, run a simulation for every single thing that we want to be different. So I think there's benefits to both, but yeah, you can learn a lot from just the training data set.
Yeah, very nice work. Yeah, I was also curious about how did you decide on the variability when you generated the data set, like for different properties?
Yeah, so for the pre-injection when we were, I guess still we're a little bit confined because we chose to use the 6 different composite rock types, which were developed from the previous work from GeoCquest. And then we sampled the rock types for different realizations. So they were still conditioned at the wells, but what they look like in terms of geostatistical parameters or correlation lengths is different. And that work was developed from University of Melbourne. And then we also are sampling the actual permeability, porosity data for that particular composite rock type. And so then we have a histogram of data or distribution of data for each of those rock types, and we're sampling points on the
Thank you very
curve.
much. Very, very
Great. Okay. Any other questions? All right. Well, on behalf of the Stanford Center for Carbon Storage, as well as the project team, Sally Benson, Catherine Callis, Catherine Spearin, I'd like to thank you very much for presenting your results today. And if anyone has any further questions, please feel free to reach out. Anyway, thank you all for attending, and we'll reach out next time we've got a good webinar. Thank you.
Bye-bye. Thank you.